All right, hello everybody. It is time to go over the lesson 1-4 worksheet on inductive reasoning. Now, I think this is a really fun section, but I know that it can be frustrating for some of you who are not used to dealing with lots of different topics in math in the same section. So let's go ahead and start with number 8 here. Danielle tests the following conjecture. If two angles share a common vertex, then they are adjacent. Remember, adjacent means next to each other. Her work is shown below. What error does Danielle make? So Danielle drew a diagram. She says angles that are adjacent share a vertex. This statement is true. And as you can see, she's drawn two angles that are adjacent. She said, hey, they share a vertex. But that's not what the if-then statement says here. This says if two angles share a common vertex, then they are adjacent. So we want to show that for all angles that share a common vertex, they're adjacent. However, that's not true. So here's a diagram. And here's an angle right here. And here's an angle right here. Those angles happen to share a vertex, but they are not adjacent. So she forgot about vertical angles and any other types of angles that come off of the same vertex. So she forgot about vertical and other types of angles. Types of angles. All right, so then consider the following conjecture. There are no prime numbers between 7,608 and 7,620, right? Prime numbers meaning numbers that have no factors except one and themselves. How could you show that this statement is true or false? Would it still be a conjecture if you do not find a counterexample? Explain. So how is going to do a lot of work for us here, because we don't need to show whether the statement is true or false. We would just explain how, right? So how could I find out whether these two numbers are having any prime numbers in between them? The how would be to check all the numbers. We would check all the integers, right? The whole numbers. So we would check all the integers between the two numbers, 2, and see if they have factors. Let's see if they have factors. Okay, if one doesn't have factors, if one doesn't, then it's a prime number, which would make it a counterexample. And a counterexample. And then the second question says, would it still be a conjecture if you do not find a counterexample? It absolutely would still be a conjecture. A conjecture doesn't have to have a counterexample. So it would still be a conjecture because it's still something you can test. All right. Number 12, observe the pattern made by the figures. Can you write a conjecture about the number of triangles formed by connecting one vertex of a polygon with end sides to each of the other vertexes? So they're saying if I start with a vertex and I connect it to the other vertexes, this one, how many triangles can I make? So here, with just a triangle, you're only going to be able to make one triangle. You can't cut that anymore. With a four-sided shape, of course, you're going to make two triangles. 5-sided shape will be 3 triangles, and a 6-sided shape will be 4 triangles. So when we think about the conjecture there, we see that our pattern is going to go up 1, 2, 3, 4 as our side lengths go up 3, 4, 5, 6. So the number of triangles is just going to be n, the polygon with n sides. So the number of sides minus 2, right? 4 minus 2 is 2, 5 minus 3 is 2, 4 minus 6, or 6. I'm saying that completely backwards. I'm sorry. 4 minus 2 is 2, 5 minus 2 is 3, 6 minus 2 is 4. So we could say T for triangles equals n for number of sides minus 2. All right, then number 16. Support the following conjecture with 4 examples or disprove it with a counterexample. So either we have to find 4 examples that work or a counterexample that doesn't. The quotient dividing of 2 rational numbers is a rational number. So again, rational would mean fractions or whole numbers. So we want to say if we divide 2 numbers, can we find one that's not a fraction, that's not a rational number? It can't be written as a fraction. Now there's lots of ways to make examples of this, right? 1 over 2 would work, or any whole number divided by a whole number. But there is a counterexample because we know that if you have a fraction, you cannot divide by 0. So if we take a fraction with a number on top, divide it by 0, that is a counterexample because that 8 divided by 0 is not a rational number. So 8 divided by 0 is not rational. So it is a counterexample. Okay. Number 17, data from 4 identical trials on a new sleep herb are shown in the table. What conjecture can you make about the effectiveness of the herb? So if we look at this table and we want to make a conjecture, we've got some numbers, right? We've got the total number of subjects, which varies, and the number who reported better sleep. If we want to figure out the effectiveness of this herb, we should probably be looking at, well, what is the effectiveness rate, right? How effective, what percent of people slept better? So I can do that by finding the decimal or the fraction or the percent of people who did sleep better, right? So for group A, if 55 people slept better out of 250 people, that means that 0.22 or 22% of people slept better. For group B, that'd be 35 out of 170, which is going to be 2.205 or 20.5%. And if we do 48 over 210, I'm running out of room, that is going to be 0.23 or 23%. And 40 out of 190 is going to be around 0.21 or 21%. So what conjecture can we make? Those numbers are all similar percentages, so our conjecture can be based off of that. And we can say that the herb is about 22% effective. So it's about 22% effective. All right, the next trial will have 1,000 subjects. What is a reasonable prediction for the next trial? This is just a middle school question, right? If we have a 22% effective trial with 1,000 subjects, we'll just do 1,000 times 0.22, and we find that 220 people will report better sleep. Will report better sleep. All right, plugging along here. Next, Deshawn is given the following conjecture. The first and third digits of a 3-digit number are the same if the second digit is equal to the sum of the first and third digits. Then the number must be divisible by 11. That's a lot to unpack, right? Let's think about this. Let's think about 3-digit numbers where the first and third digit are the same. The first one of those would be 100 something 1, and there'd be a third digit in the middle there. And it says if the second digit is equal to the sum of the first and third digits, then we can take the first digit 1, the third digit 1, we add those up, it's 2. So that number 121 is one of the possible numbers, right? You can see where this is going. 200 something 2, we add the 2 and the 2. 242 is possible. 363 is possible. 484 is possible. However, 5,105 is not possible because this is a 3-digit number. So that goes away. So there are actually only 4 possibilities. So when it says how can he determine whether the conjecture is true, he just needs to take these 4 numbers and divide them by 11 to see whether the number must be divisible by 11. So check to see if they're divisible by 11, right? So check to see if these are divisible by 11. If they are, right? If they are, then the conjecture is true. Then the conjecture is true. All right. Here's an interesting problem. A graphic designer wants to know the number of regions that are formed when circles overlap in a particular way. Can she find a rule that describes, that's not going to be recognized as a rectangle. Let me try that again. Can she find a rule that describes how the number of regions increases when any other circle is added to the design? How many regions would a design with 6 circles create? So of course we have 1 circle, 2 circles, 3 circles, 4 circles, and 5 circles, and they tell us that would be 1 area that's shaded, right? 3 areas, 7 areas, etc. And so we have to find a rule. Now remember, a rule can be algebraic, like some of the examples we did in class, or it could be a rule that's just like, I don't know, just in words, I guess. So if we figure out how we could say it, we might notice that 1 plus 2 is 3, 3 plus 4 is 7, 7 plus 6 is 13, and 13 plus 8 is 21. And we say, hey, the difference between the number of regions increases by 2 every time, right? Plus 2, plus 4, plus 6, plus 8, and so on and so forth. So we could write that as our rule. That's fine. The difference increases by 2 each time, right? And so if we had a 6th, we could say 6 regions would be 21, or sorry, not 6 regions. I totally did that. Opposite of what I meant. 6 circles would make 21 plus 10, or 31 regions. If you wanted to get really ambitious, there is also an algebraic formula you can use as the rule that describes the number of regions. You don't need to know how to do this, but if you're interested, any pattern that goes up by a continuing number every time, where it increases by the same thing every time, that is going to be a quadratic. So something with an x squared or an n squared, in this case for number of circles. In this particular one, it's n squared minus n, plus 1. So for example, for 2 circles, it'd be 2 squared minus 2 plus 1 would give you the 3 regions. For 5 circles, it'd be 5 squared minus 5 plus 1 would give you 21 regions. Now, of course, you don't need to know this. All right, this is just an interesting idea. It's something that you might be able to do kind of later on. Whoa, that is not even a little bit what I meant. Kind of later on, I didn't even know you could do that in math, but not anything you need to do right now. One day I'll draw a rectangle that Notability recognizes as a rectangle, and that will be a wonderful, glorious day. There we go. Okay, next, almost done. Consider the conjecture, any number divisible by 2 is also divisible by 4. Is each number a counterexample of the conjecture? Right? In order to be a counterexample, it has to follow the first part and be divisible by 2, but not follow the second part, not be divisible by 4. So let's see, 12. 12 is divisible by 2. That works. But it is also divisible by 4. So it's not a counterexample. 19 is not divisible by 2. So it doesn't fulfill the first part of the statement. So it's not a counterexample. 22 is divisible by 2. It's not divisible by 4. So that is a counterexample for the statement. 28 is divisible by 2, but also 4. So that's not a counterexample. And 30 is divisible by 2, but not by 4. So 30 is a counterexample. 22, how many dots are in the nth term of the following sequence? So the nth term in this case is going to make this, let's see, first term, second term, third term, fourth term, and our dots go 3, 5, 7, 9. It's pretty easy to tell that this is a linear function pattern with a slope of 2. That makes this a pretty simple question. It's going to be 2n plus 1 for the function rule there. All right, so thank you, everybody. Hopefully that worked well for you. If you've got any questions, let me know, and have a wonderful day.